This packet of notes, which we went over in the first day of talking about electron configurations, is all about how light relates to electrons and how we used light to discover the different structures that electrons use inside the atom. So we start off with a little story. The weather was sunny on Saturday, so we decided to go to the beach. Unfortunately, I forgot to put on sunblock and my shoulders got burned. On Sunday, it was raining, so we drove home. I helped my dad with the map and listened to music on the radio. That evening, we rented some DVDs and my mom popped some microwave popcorn. My little brother kept grabbing the remote control and pressing the fast forward button when he got bored with the movie. On Monday morning, the weather was good. The sky was clear and blue. My dad and I were playing soccer in the backyard when he fell and twisted his ankle. He went to the hospital to get an x-ray. The doctor said that his ankle wasn't broken. Now, there are 6 different types of electromagnetic radiation referenced in that story, in that paragraph. And what we're going to do is identify each one of them. Let's go to the easy one. Ultraviolet light. Okay, ultraviolet light's referenced anytime that we go outside, because ultraviolet light is what causes you to get a sunburn. Okay, so that's ultraviolet light, and that's going to be F there. Okay. The other easy ones, well, if you went to the hospital to get an x-ray to see about the ankle, we're pretty sure that that's checking to see that the ankle wasn't broken. Okay. Visible light, you're looking at the color of the sky. Radio waves, you're listening to the radio in the car. Okay, you're listening to the radio, okay, because it broadcasts along radio frequency. Microwaves help you make popcorn in your microwave oven. Okay, so the fun thing about the microwaves is they actually broadcast. Our microwave is the part of the spectrum which you use in the microwave oven. Also, is what you use in your cell phone. Your cell phone broadcasts as part of the microwave spectrum. Look it up on YouTube. There's a video, several videos of popping popcorn using cell phones. Pretty cool. Lastly, using the remote control for the DVD player. That is infrared. Okay. Now, what we've got to do is try and arrange the different forms of electromagnetic radiation in order from lowest energy to highest energy. So the only way that these all differ is because they have different energies. Otherwise, they're pretty much exactly the same form of stuff. All right, they're pretty much the same. So let's start off with visible light here. We can look at light all day, and it's not going to hurt us. But if we go outside for too long, we do get a sunburn. So ultraviolet is probably going to be somewhere up here. Okay, so that's ultraviolet. Okay, we're not really sure where it is, and I'm not going to tell you exactly. Okay, X-rays can also go all the way through you without even getting stopped. Okay, ultraviolet, at least it's going to stop at your skin and hurt you there. But X-rays can go all the way through you. All right, they just get stopped by your bones. So maybe X-rays are up here. Now down here, lowest up to highest in terms of what's lower the energy than visible light. We've still got radio, we've still got microwaves, and we've still got infrared. Okay. Now I'm going to put the infrared that way close because it's got this word red, which I know is a color that we might see. All right, so I'm thinking that maybe that has something to do with our visible light here. I'm not going to tell you which one goes where, we're just going to figure that out later. Now here, they travel in waves. All these types of electromagnetic radiation travel in waves. 2 important properties are wavelength and frequency. Okay. The wavelength is the horizontal distance from one crest to another crest. So here, if I want to go from this crest to this crest, that would be a distance of 1 wavelength. It also works going from trough to trough. That would be 1 wavelength. You could even go from the center of a slope to the center of an identical looking slope. That would also be 1 wavelength. Okay, so 1 wavelength is just a line, the distance from a point on a line until the line looks identical. Okay, so next page. And we'll move this down so we can see it a little bit better. the frequency of a wave represents the number of waves that pass by a fixed point per second. So if I'm standing on a pier at the beach and I'm watching the waves roll into shore, okay? So let's say I'm standing here. There I am, okay? I'm watching this wave come in towards shore, and I'm counting how many I see per second. Compared to standing here, watching these waves roll into shore. Which one am I going to see more of? I'm going to see more of wave B come by, okay, because the waves are closer together. It's got a shorter wavelength. Here's the other thing that we know about frequency, all right? So wave B, higher frequency, shorter wavelength. We also know the higher the energy, the higher the frequency. So that's an important little bit of knowledge. With that, we can relate energy, frequency, and wavelength. If energy is high, frequency will be high, and wavelength will be short, like in wave B there. If energy is low, frequency will be low, wavelength will be long. You can think about wave A here, having a nice low energy because it's all stretched out. Okay, it's stretched out, it's relaxed, it's got low energy. So let's see what we know about here. Wave B has a something energy. Well, we look at wave B. It's got a much shorter wavelength, which actually is a question here. It's got a much shorter wavelength. So we find short wavelength on here and see what that means about frequency and energy. Short wavelength, high energy. So wave B has a higher energy. If it's got a higher energy, it also has a higher frequency. Put that in there. Now let's go and talk about some of the individual types of electromagnetic radiation in terms of wavelength, frequency, and energy. Radio waves down here, low energy. Ultraviolet, relatively high energy. So radio with a low energy will also have a longer wavelength. X-rays, being here higher energy than microwaves. High energy means high frequency. So X-rays have a higher frequency than microwaves. Infrared light here has lower energy than visible light. And down to the part of the spectrum that we actually care about, the visible spectrum. Remember the abbreviation Roy G. Biv. Okay, well, red, orange, yellow, green, blue, indigo, violet. Well, that helps us out because infrared is just below red. Infra kind of means inside or under. Okay, that's infra. Ultra violet means over or above. Okay, so if we ever get confused, infrared, under red, ultraviolet, over violet, and that helps us arrange the energies of our light. So, red light has a lower energy than green light, which means it has a longer wavelength. Violet light has a higher energy, so it has a higher frequency. Blue light here has a higher energy than orange light. Okay, and next page. So I know we're now talking about light and all that. We're supposed to be talking about electrons. Well, here's how it works. You get a neon sign, fill a glass tube with neon gas, and then you run electricity through that tube. When the electricity is turned on, the gas glows. Why? So the deal is, electrons exist on different energy levels. When we've got low energy, generally people want to lay down, okay? If they can't lay down, they're going to sit down. And if there's no chairs, they're just going to sit on the floor or on something that we call the ground, okay? Electrons are the same way. They're lazy. They hate having energy. When they are just at peace, they're sitting in what we call the ground state. That is low energy, okay? Low energy, okay? Well, what happens next to the electrons in that neon gas? Somebody switches on the current, okay? And all of a sudden, they go, whoa! They absorb energy, all right? So that's what happens. Somebody switch on the current, and they absorb energy. So what happens, this is kind of like what happens to a 4 or 5-year-old after eating a bunch of candy. They get hyper, they get crazy, they get something that we call excited. Excited states are higher energy. Okay, excited states are higher energy than the ground state. So these electrons that have been sitting in their ground state, all of a sudden, somebody turns on the current, they absorb a bunch of energy, and they jump up into an excited state. Well, electrons are very lazy. Electrons hate having high amounts of energy, so they want to get rid of their energy. So what happens? The excited electron falls back down towards the ground state. And as it does it, it releases energy. Now, it releases energy as a wave. It releases energy as a wave. Releases energy as light. So, electrons in a gas tube, in a neon light. They start out in the ground state around their atoms. Somebody switches on the current. They absorb all that energy. They're up in an excited state. They're hyper. They're running around. They're saying, oh no, I don't want any energy anymore. So they release that energy. They go back down to the ground state. That energy they release it as light. Okay? So, what happens? What happens here? If that light is, or if that gas is hydrogen, we see a pink color. And when we hold it up to a prism, that light is being separated into 4 different colors. Okay, that's different from regular sunlight, where it separates out into the entire spectrum. Hydrogen is very specific, and only 4 different colors that we can see. Okay, violet, blue, green, and red. And now remember, red light has a lower energy than violet light. Okay, and this is very important. Electrons release energy when they fall from excited state to the ground state. Okay, so let's look at the next page. In the diagram below, electrons are falling from excited states down to the ground state. Ground state here, first energy level. First energy level, which is the lowest energy level. Here's the second, and third, and the fourth, and the fifth. Okay? So, ground state, lowest energy level. As this thing falls from the 5th energy level down to the 1st, it's got a lot of energy to get rid of. Each one of these energy levels is higher and higher and higher. As it drops down, it's going to release all of that energy. So this is going to release a lot of energy. The light that with the highest amount of energy to carry it away is violet. So this is going to be violet light, releasing the most energy. Over here, where it only has to drop 1 energy level, this would be red, with the least amount of energy. And then this would be green and blue, okay? Increasing in amounts of energy. As the electron falls more and more energy levels, it has to release more and more. Now, the idea here came up with Niels Bohr. He's the guy who came up with this idea that electrons not only at energy levels, but those energy levels are basically orbits. We have the first energy level, we have the second energy level, the third, and the fourth, with the first energy level being the ground state. Okay? As electrons get closer to the nucleus, they get lower and lower in energy. As they get further away, they get higher and higher in energy. So, for an electron to transition from the third to the first energy level, it would have to release some light. Okay? When an electron is its lowest energy orbit, it is in the ground state, and that is close to the nucleus. Okay? Bohr suggested an electron in the ground state could jump to a higher energy level when it absorbs energy, just like when the electrons in that gas tube absorbed the energy from flipping on the current. He also said that electrons could fall from a higher energy level to a lower energy level, which would release energy, and we would see that as light.